All right, so today we're diving into a topic that sounds like something straight out of science fiction,
Oh, I know it.
but it's actually real, and
Mm.
it's all about superconductivity.
Yeah.
And, it's something that you and I have both been kind of fascinated by over the years.
Oh, yeah, for sure.
And we're going to try to uncover, what is it about superconductivity that makes it so interesting?
Right.
For our listeners out there who are really into the hardcore science,
Yeah, the nitty-gritty.
the nitty-gritty, yeah.
Yeah.
So we'll talk about some of the basic things that people probably already know, like Ohm's law and resistance and things like that.
Right.
But we're also going to get into some of the deeper stuff, like Cooper pairs,
Yeah,
energy gaps,
absolutely.
and things like that, and also touch on why this stuff is so amazing.
Right.
Like it really could change the world.
Oh, absolutely.
So I guess to start out, I mean, maybe we should just I don't know. Yeah, just jump right in.
Jump right in, yeah.
Yeah.
When we talk about superconductivity, I mean, the first thing that comes to mind is
Zero resistance.
zero resistance,
Yeah.
right? So, people, a lot of people listening probably remember
Ohm's law.
Ohm's law, yeah, from high school or whatever.
Sure.
So, with Ohm's law, we have voltage is equal to
Current times resistance.
current times resistance.
Right.
And resistance is kind of like the,
It's like the friction.
yeah, it's the friction
Except in the wire.
in the wire,
Uh-huh.
So if you have like a water pipe, it's like the
roughness of the pipe.
roughness of the pipe.
Yeah.
And so what's amazing about superconductors is
That resistance goes to zero,
it completely goes to zero.
which is just mind-blowing when you think about it.
Yeah, I mean, it's like, imagine like a river suddenly having
No friction at all.
no friction at all,
Yeah.
It's like, how is that even possible,
Yeah.
right? Yeah, so you could just like set a boat in the river and it would just
You would just keep going.
keep going forever.
Forever, yeah.
Yeah, it's crazy.
So, how does that happen?
Well, that's where the quantum mechanics comes in.
Okay.
And it all has to do with these things called Cooper pairs.
Cooper pairs. Okay.
So, normally electrons,
they don't like each other.
they hate each other. They want to be as far apart as possible.
They're antisocial.
They're antisocial little particles.
Yeah.
But when you cool a material down to super low temperatures, something really weird happens.
They start to pair up.
They start to pair up.
Okay.
And they form these things called Cooper pairs. And these pairs, they act like one entity.
Oh, wow.
And they can move through the material without any resistance whatsoever.
So it's kind of like if you had, a dance floor,
Oh, I like that.
and it was really crowded, and everybody was bumping into each other,
Uh-huh.
but then suddenly,
Everyone pairs up.
everyone pairs up, right?
Right.
And they start moving in unison,
Yeah, and they can just glide across the dance floor.
and they don't bump into each other.
No bumping, no friction.
So, what causes them to pair up?
So the dance floor in this case is the material's lattice structure.
Okay.
And the force that couples these electrons together is due to interactions with vibrations in the lattice
Okay.
called phonons.
Phonons.
And so these phonons, they're like little matchmakers.
Okay.
They help the electrons overcome their repulsion and form these pairs.
Wow, so the phonons are like little cupids.
Yeah, you could think of it that way.
Yeah, that's a great analogy.
It's a quantum love story.
Yeah.
Yeah,
So these Cooper pairs are the key to zero resistance.
that's right.
They can move through the material without losing any energy.
Exactly.
And this is where the BCS theory comes in.
Right.
Named after Bardeen, Cooper, and Schrieffer.
3 brilliant physicists who won the Nobel Prize for this.
Yeah, they figured out.
They figured out how these Cooper pairs behave.
Yeah.
And they showed how these pairs can explain the observed zero resistance.
So they basically explained how superconductivity works.
Exactly.
At least at the,
At the fundamental level.
Yeah.
Yeah.
So, we've been talking about zero resistance,
Right.
but there's another really cool thing about superconductors.
Yeah, the Meissner effect.
The Meissner effect, right?
Yeah.
So what is that?
So the Meissner effect is the expulsion of magnetic fields from the interior of a superconductor.
So they basically repel magnetic fields.
Exactly.
It's kind of like, I don't know, like if a celebrity walked into a room
Oh, I like this.
and everyone,
Everyone just cleared a path.
yeah, cleared a path around them.
That's a great way to put it.
So the magnetic field just kind of goes,
Goes around the superconductor.
yeah.
Yeah.
And this is what allows for things like maglev trains to actually levitate.
Yeah, because you have these magnets on the train and magnets on the track, and they repel each other.
And it just floats.
It flows.
And it can go incredibly fast.
Oh, yeah, like hundreds of miles per hour.
Hundreds of miles per hour.
Yeah.
I mean, that's just amazing, right?
Yeah.
So, what are some of the other potential applications of superconductivity?
Well, I mean, you've got things like lossless power transmission.
Okay.
So, right now when we transmit electricity over long distances, we lose a lot of energy.
As heat.
As heat, yeah, due to resistance in the wire.
With superconductors.
No resistance.
Yeah.
No loss.
But we could save a ton of energy.
A ton of energy.
And money.
And money.
And reduce our carbon footprint.
Exactly.
That's amazing.
And then you've got quantum computers.
Oh, yeah, quantum computers.
Which are using superconducting circuits to maintain these really delicate quantum states.
That are essential for computation.
And that could revolutionize fields like medicine, materials science, artificial intelligence.
Yeah. I mean, it's hard to even imagine.
It's hard to even fathom.
Yeah, what we could do with that.
Yeah.
It's incredible.
Yeah.
But there must be some challenges, right?
Oh, absolutely.
I mean, it can't be all,
It sounds too good to be true.
Yeah, too good to be true.
The biggest challenge is the low temperatures required.
Okay.
Most materials only become superconducting at extremely low temperatures.
Like close to absolute zero.
Yeah, like close to absolute zero.
Which is, negative 400 and something degrees Fahrenheit.
Yeah, it's incredibly cold.
And that's not easy to achieve.
No, and it's very expensive to maintain.
So that's kind of a big roadblock.
It's a big hurdle.
Yeah.
But researchers are working on finding materials that can superconduct at higher temperatures.
Oh, really?
Yeah, so-called high-temperature superconductors.
And how high are we talking?
Well, they're still pretty cold.
Okay.
But they're getting warmer all the time.
So we may not have room temperature superconductivity yet?
Not yet.
But it's not out of the realm of possibility?
No, not at all.
That would be amazing.
That would be revolutionary.
Yeah. Well, I think this has been a really fascinating deep dive into the world of superconductivity.
Yeah, it's been fun.
We've talked about how electrons pair up to form Cooper pairs.
Right.
And how these pairs can move through material with zero resistance.
Thanks to those matchmaking phonons.
Yeah, those matchmaking phonons, right?
Yeah.
And we've talked about the Meissner effect
Yeah.
and how it could be used for things like maglev trains.
Yeah, and all sorts of other cool applications.
Yeah, and we've also talked about some of the challenges.
Right.
Like the need for extremely low temperatures.
Right.
But, who knows what the future holds?
Yeah, the future is bright.
Yeah, maybe one of our listeners out there will be the one to discover room temperature superconductivity.
That would be incredible.
It would change the world.
Yeah, it would be a whole new era.
So keep dreaming big, and thanks for listening.
Thanks for having me.
It's been a pleasure.
Yeah, likewise.
And we'll see you next time
See you later.
for another deep dive.
Into the world of science.
Yeah.
Right. Bye.